All right, so in this last section of this chapter, we're going to go over a new type of random variable called binomial random variables and geometric random variables. So they're similar, kind of like what we've been doing, but different in a couple key ways. So let's look at these scenarios to kind of get a sense of what's going on. So we have like a coin, we're tossing 5 times, we're going to count the number of heads, something pretty normal. A roulette wheel, so when you guys go to Vegas, you want to gamble, you're going to spin it, get red, get black, that sort of thing. So you want to record the number of times the ball lands in a red slot. And the third one, maybe you end up being a nurse and you're at a hospital and you have all these babies being born, and you take a sample of 100 babies, and you're going to count the number of females. And so these are like, well, what do all these have in common? Well, think about it in math sense, not like not like a social setting sort of thing. Let's think about what they all deal with mathematically. So we toss a coin 5 times, spin a roulette wheel 8 times, take a random sample of 100 babies, count the number of females. So these are actually all binomial random variables. Now it's like, well, why are they that? Well, they satisfy these 4 conditions. They satisfy the condition of being binary, meaning that you can have a clear definition for success or failure. So like for the first one, a success is a heads, a failure is not a heads or a tail. So for the roulette wheel, success is getting a red slot. A failure is getting not a red slot, it could get black or green. And for the babies, 100 babies, the success is getting a female. A failure is getting a, not a female. So it satisfies, that's the binary condition. They also satisfy what's called an independence condition, meaning that if you know the outcome of one of the events or one of the individuals going on, one of the trials, we say, it doesn't tell you anything about the probability of the other one. So if you toss a coin 5 times and you know that the first one is heads, that's not going to tell anything about what the chances are the second coin is going to be heads, or the third one, because they're independent. It doesn't matter. It's not going to change. Same thing with the roulette wheel. You get red, the first 2 times, doesn't mean you're going to have a higher or lower chance of getting red the third time. They're independent. And same thing with babies. If you have you check the first 10 babies and they're all females, even though in your head you may think, oh, the next one has to be a male, it's not going to change the chance that the next baby is going to be a female or male. The probabilities of each event are independent. The third condition is that they all have a fixed number of trials ahead. We're set that we're going to toss a coin 5 times, so 5 trials, spin a roulette wheel 8 times, so 8 trials, and then take a sample of 100 babies, so 100. And then the success condition, the probability of having a success is the same on each trial, so we call that P for probability. Getting a heads is always 50% or 1/2. Getting a red, it's not actually 1/2. It's usually like, depending on the roulette wheel, they usually have red, black, and green, but it's usually closer to 1/2. It's sometimes like 18 out of 37, 18 out of 39, something like that. But it's the same on every turn though. That's what matters. And then take a random sample of 100 babies, count the number of females. It's always, well, I think it's actually that there's 51% of people are females, but it's always, again, it's always the same chance. The success chance is always the same. So these 4 conditions, when met, mean that a variable is a binomial random variable. And a good acronym to remember what conditions you have to meet is to remember the word bins, binary, independence, number, and the success condition. All right, so let's go through some examples. It's always good to learn this stuff. Now, there's a formal, more rigorous definition. This is kind of the one I had in the textbook I use. It's more user-friendly, but it's more wordy. But it's just another way of formally saying when you have a binomial random variable with a binomial distribution. So we say that a random variable is binomial and it has parameters. So we use lowercase n for the number of trials, lowercase p for the probability chance, capital X to represent the success. So like the trial happening. And we have whole numbers, you know, like being 0, 1, 2, 3, 4, because you can have 1 success, 2, 3. You can't have like 2.5, 3.5, or 2.5. Well, let's go through a practice problem. So here we're going to see which of these variables have a binomial distribution. So think to yourself right now. Let's look at the first one. We have a fair die. We're going to roll it 10 times, and we're going to let x be the number of 6s. But this counts as being a random variable with a binomial distribution. So let's check each condition. The binary condition, you know, you can roll a die and either you get a 6 or you don't get a 6. Don't be like failures, you know, 5 or 4. Don't make like 6 possibilities. You know, it's either a success if it gets a 6 or a failure if not a 6, or if it's not a 6. But there are, you know, again, there's 5 ways to not get a 6, but it's still just like one event. So it satisfies the binary condition. Independence condition. If you're rolling a die 10 times, what your result is on the first toss doesn't tell you anything about the second toss or third toss or anything like that, because the chances are always the same. It's always going to be 1/6 if the die is fair. So it satisfies that. The success condition. So, well, not the number condition next. Do we have a, you know, fixed number of trials stated beforehand? And we do. We were told that we're going to roll it 10 times. So we have n is 10. And then now the success condition. Is the probability of success always the same? And, you know, if it's fair, it's always going to be 1/6, because there's, you know, 6 possibilities. And so then the independent condition is met. And then since all the conditions are met, this will qualify as a binomial random variable. All right, let's look at the second scenario. We're going to shoot a basketball 20 times from various distances on the court. And we're going to let y be the number of shots made. So let's think for a second. So first, does it satisfy the binary condition? What would a success and failure be? And a success would be that you made the shot. A failure is that you didn't make the shot. You can miss a shot in so many different ways, but you have just those 2 things, making it or missing it. So you got the binary condition met. So we're good there. Now you get to think, is the independence condition met? Is your chance of making a shot going to be affected by whether or not you made the previous shot? And, you know, technically, you know, it shouldn't be. I guess you can argue in real life. You know, people like to say they get on fire if they're making shots because they get more confidence. But technically, if you make a shot, make a 3-pointer, it's not going to change your chance of making the next 3-pointer because each shot is independent. So it meets the independent condition. Now the number condition. Do we have a fixed number of trials beforehand? And we're told that you're going to shoot the basketball 20 times. So yeah, you got the number condition met because you're told 20 times. So your number of trials is 20. So that's met. Now is the success condition met? Well, now let's think. If you're going to shoot a basketball, it says various distances. It doesn't say always from the free throw or always from the 3-point line. So it's various distances. You know, if you're a human, I assume, you're going to have different chances of making a shot. You know, whether it's a free throw, a 3-pointer, a layup, a half court, the probability is going to change. So then the success condition is not met because you don't have the same chance of making a shot from every point on the court. So just because that one condition isn't met, it's not going to be a binomial random variable. It has to meet all 4 or it doesn't count. All right, and let's look at one more. Observe the next 100 cars that go by and let C equal the color. Well, let's think about this. If we're going to let C equal the color, will it satisfy the binary condition? What would qualify as a success and what would qualify as a failure? So let's think for a second. Well, if we're just recording color, you could be, it could be red, it could be blue, it could be whatever, polka dot, purple. What we're not told to count like number of reds or blacks or white cards. So this is not even going to meet the binary condition because you don't have a clear success failure that you're going to have your actions fall into. So then right away it's going to fail. So it's going to fail, and then C, this is not going to count as a binomial random variable, so we don't have to go and check any of the other ones.